G'day, John here. Welcome to another PyProx tutorial, helping you understand the impact of uncertainty in data and simulation. In the next few minutes, I'm going to teach you how to use multi-level Monte Carlo quadrature, MLMC for short, to compute the mean of a computationally expensive high-fidelity model prediction using a hierarchy of low-fidelity models with unknown means. I'll also teach you how to optimize the number of samples used to evaluate each model with the goal of minimizing the estimated budget. And I'll conclude by summarizing some important theoretical properties of multi-level Monte Carlo estimators when they are applied to numerical models with discretization errors with known convergence rates. MLMC estimators, or ML estimators, can be used to efficiently estimate the mean of a high-fidelity model using a hierarchy of low-fidelity models. Such hierarchies can be attained, for example, by solving a PDE on increasingly finer spatial meshes. In this tutorial, we'll follow standard practice when using multi-level Monte Carlo estimators and order the models by increasing fidelity so that F0 is the lowest fidelity model and Fm is the highest fidelity model. But be careful, this ordering is different to the ordering used by most other Monte Carlo estimator tutorials that I've presented. The ML estimator takes the form of a telescoping sum, and unlike control rate Monte Carlo CVMC, evaluates each model at each set of samples. For example, the first term requires the evaluation of the multi-fidelity model at the set Z0, and the second term requires the evaluation of the lowest fidelity model and the next model in the hierarchy using the set Z1, and so on. Moving forward, I'll use the notation capital Z without a subscript to denote all such sets Z0 through Zm. Multi-level estimators can be constructed using a three-step procedure. Step 1 randomly generates n+1 sets of independent samples Z0 through Zm from the joint density of the random variable Z. The size of each set is determined by the integers n0 through n respectively. Later in this tutorial, I'll discuss how to optimize these values of n. Because each set is generated independently, the probability that any two sets contains one or more of the same samples is 0. I use the notation that the intersection of Zm and Zn is empty if m not equals n to make this property clear. Step 2 evaluates all the models on the correct set of samples. The independence of sets is depicted by the bottom left figure. Different rows and colors represent different independent sets. The sets used to evaluate each model are listed in each column. For example, the lowest fidelity model F0 is evaluated at the sets Z0 and Z1. An example of such sets is shown in the middle figure. The model F0 is evaluated at all the samples in these two sets, yielding the evaluation shown in black in the far right figure. Similarly, F1 is evaluated at the grey and red samples Z1 and Z2 to produce the values in green on the far right. All models are evaluated on exactly two sets, except the highest fidelity model, which is only evaluated on the last set, in this example, the set Z2 in red. The values of F2 on these samples are shown in cyan in the right figure. Finally, in step 3, we use the model values we generated to estimate the mean of the high fidelity model by constructing the estimator shown on the slide. The colors here show where each of the independent sample sets that we introduced earlier are used in the telescoping sum. ML estimators are designed to reduce the computational cost of computing the mean of a high fidelity model. However, so far I've only shown you how to build the ML estimator using a given number of samples n0 through nm. In practice, we should choose the number of samples to minimize the computational cost of the ML estimator needed to obtain an estimated variance equal to a predefined threshold epsilon squared. The formal definition of this optimization is shown on the slide. The optimization problem minimizes the computational cost of the estimator, which depends on the number of times each model is run, and thus in turn on the numbers n0 through nm. I will detail this optimization problem in the theory section of this tutorial. However, if you only want to use multi-level Monte Carlo and not understand the theory, you must know that solving the optimization problem requires two steps. These two steps must occur before the estimator is constructed with steps 1 through 3. The first pre-step is to use a pilot study to approximate the variances of the differences between consecutive pairs of models. In short, a pilot study uses a small number of samples to compute the variances. However, you can find more details on how to execute a pilot study in another tutorial. The second pre-step involves computing the solution of the optimization problem. Fortunately, when using ML estimators, the optimal solution can be attained analytically. The expression for the optimal Nm is given in the last equation. It depends on the target tolerance epsilon and the computational cost of simulating model M once, that is W underscore m and the variance v underscore m. In some previous tutorials, I showed you how to use control-variate Monte Carlo estimators to estimate the mean of a high-fidelity model using low-fidelity models with known means. However, in practice, we may not know the mean of the low-fidelity models. Multi-level Monte Carlo was the first attempt using variance reduction to use low-fidelity models with unknown means. Multi-level estimators are motivated by three observations. First, the expectation of the model Fm can be expressed as the telescoping sum shown for any sequence of models. Secondly, the area in many numerical models converges as the numerical discretization is refined, such that the variance of the difference between consecutive model discretizations converges to zero. The third observation is that the cost of the numerical model increases with fidelity, so that estimating the mean of a model discretization becomes more computationally demanding as the model fidelity increases. Similar to the previous tutorials, I'll use W underscore m to denote the cost of evaluating the mth model. The form of multi-level estimators is based on the observation that the mean of the high-fidelity model can be expressed as a telescoping sum. The MLM estimators approximate the mean of each term in the sum using Monte Carlo estimators. As shown previously and by the figure, each model is evaluated exactly twice at each set of independent samples, except the highest fidelity model, which is evaluated only once. Again, here colors represent independent sample sets. Consequently, the computational cost of evaluating an LM estimator is the cost of evaluating the highest fidelity model at n capital M samples, plus the cost of evaluating models lower score m and m minus 1 at n underscore m samples from n equals 0 to m minus 1. The figures on this slide compare the independent sample preditions used by control-variate Monte Carlo and multi-level Monte Carlo estimators. CV estimators require evaluating all models at one and only one of the same set of samples. In contrast, multi-level estimators evaluate models at different sets of samples. This makes minimizing the variance of ML estimators by optimizing the number of samples used to evaluate each model more difficult than the minimization used for control-variate estimators. The variance of a multi-level estimator is simply the sum of the variances of each term in the telescoping sum. I leave it to the viewer to derive the form of the variance shown using the techniques presented in the control-variate tutorials. Under the assumptions that the computational cost of evaluating a model at a single sample z increases as the fidelity increases, then it is relatively inexpensive to evaluate the first term in the sum, which only needs evaluations of the cheapest model. Thus we can make the variance contribution from the first term small. Now, under the assumption that the variance of the differences between models goes to zero when the models are sufficiently refined, the variance between two consecutive pairs of models will also decrease with fidelity. This means that while we cannot afford as many samples of the differences, say in the second term, the variance of the second term will be smaller than the variance of the second model. Control-variate methods assume that the highest fidelity model is unbiased. This is useful when a trusted high-fidelity model is available and its discretization cannot be refined further. However, multi-level methods are often used assuming that the numerical model can be refined indefinitely. Consequently, the mean squared error of multi-level estimators is the sum of the squared bias of the model M, which I'm going to call epsilon squared, and the variance of the ML estimator. In the control-variate setting, we minimize the estimated variance subject to the cost of the estimator being less than the total budget W max. However, in the ML setting, we can also minimize the computational budget such that the variance of the estimator is equal to the bias squared. This slot-out optimization problem is shown on the slide. It is important to note here that solving this optimization problem requires estimates of the variances V underscore M. Typically, these variances must be estimated using a pilot study. You can find more information on how to conduct a pilot study in another tutorial. One nice property of MLMC is that the optimal number of samples of each independent sample prediction can be optimized analytically. The optimal number of samples is shown on the right. Look out for another tutorial deriving this optimal solution. The expression for the optimal NM depends on the target tolerant epsilon, the computational cost of simulating model M once, that is W underscore M, and the variance V underscore M. If you want a smaller variance, the number of model evaluations increases, which makes sense. Similarly, cost increases as the work needed to evaluate a model increases. In contrast, NM decreases as the variance of the difference between models decreases. If the assumptions I introduced earlier hold, so that the variance Vm decreases quickly relative to the increase in model cost Wm, the cost of the ML estimator will be much more computationally efficient than a single Monte Carlo estimator. On this slide, the left figure plots the optimal number of samples allocated to each model when using an idealized 5-model hierarchy for different target costs Wmax. The numbers in the different colored boxes represent the total number of evaluations of each model. The relative size of each box represents the fraction of the total computational budget that is allocated to evaluating each model. In the figure, I use the control variate model ordering to be consistent with similar plots I presented in other control variate based tutorials. This means that smallest number of samples are allocated to F0, which denotes the highest fidelity model. Yet despite F0 being evaluated the fewest times, its evaluation represents the biggest fraction of the computational budget. The general trend is that more evaluations are given to cheaper models, reflecting that this problem satisfies the assumptions made by multi-level Monte Carlo that I introduced earlier. The variance of the estimator for each target cost is shown on the right. Just like single fidelity Monte Carlo, labeled MC, the variance decreases linearly with the target cost. However, for a given target cost, the variance of the MLMC estimator is over an order of magnitude smaller than the Monte Carlo estimator variance. Just like control variate Monte Carlo, the relative performance of Monte Carlo and multi-level Monte Carlo depends on the correlation between models and their relative costs. Indeed, the relative performance of control variate Monte Carlo and multi-level Monte Carlo depends on the same factors. You should look out for another tutorial on how to practically choose the best estimator for a given problem using a pilot study. When multi-level Monte Carlo is used with models that have well-known convergent properties, we can bound the total amount of computational work required to obtain an ML estimator variance equal to a prescribed squared bias epsilon squared. For example, such rates may be omitted by finite element models as the spatial mesh is refined using a procedure similar to that depicted on the right. The theorem on this page formalizes the result, which applies when 3 conditions listed are met. Specifically, the cost of evaluating model M once increases at a rate proportional to 2 to the power of m times gamma. Secondly, the variance of the difference between models decays at a rate proportional to 2 to the power of m times beta. And third, the magnitude of the bias of the model M decays at a rate proportional to 2 to the power of m times a half times the minimum of gamma and beta. If these conditions hold, then the expected computational budget needed to achieve the desired variance is bounded above by 3 cases. The relevant case depends on the relative values of gamma and beta. This theorem is a really nice result that rigorously demonstrates the utility of multi-level Monte Carlo estimators. Unfortunately, the condition needed by this theorem cannot be established for many applications. For example, the 3 conditions will not hold if a model hierarchy is based on improving physics fidelity, for example, moving from Euler equations of flow to Navier-Stokes equations in an ensemble. They may not even hold when refining the discretization of a single physics model, for example, when refining the mesh does not monotonically decrease the model bias. That brings me to the end of yet another PyRox tutorial. Hopefully you now understand how to construct multi-level Monte Carlo estimators and some of their most important properties. What I'd like you to understand is 1, that MLMC estimators can officially estimate the mean of a high-fidelity model using a hierarchy of low-fidelity models. 2, that MLMC is best suited to the situation when model discretizations can be continually improved so that asymptotically the model bias goes to 0. 3, we can analytically optimize the number of samples of each model to minimize the computational budget, subject to the estimated variance being equal to a specified value. And 4, the form of ML estimators emits strong theoretical guarantees, provided certain conditions are met. See you next time.